Welcome to our first remote video lesson for Earth Science Summer School. This is about Earth's interior and the theory of plate tectonics. Okay, so to start our discussion on the interior of the Earth, we have to talk about the layers of the Earth. We can group the layers of the Earth by composition, so what the layers are made out of. First would be the crust that's on the outside. The crust is made of two types of rocks. Basically, there's continental crust that's made out of granite, which is a familiar type of rock. A lot of times countertops are made out of that. The density of granite is about 2.7 grams per centimeter cubed. There's also oceanic crust, which is made out of a rock called basalt. This has a density of 3.0 grams per centimeter cubed, so a little bit higher than the continental crust density. We have the mantle of the Earth, which is like the middle portion here. The mantle is made out of a rock called peridotite. The density of the mantle is 3.4 grams per centimeter cubed. And then we have the core. The core is made out of iron and nickel, and it has a density of about 13 grams per centimeter cubed. So you can see that as you move from the outside towards the inside, the density increases significantly. Another way that we can describe the layers of the Earth is based on their physical properties. So if we do it this way, the first layer on the outside is called the lithosphere. It's a cool, rigid shell that averages about 100 kilometers in thickness. However, some portions are much thicker or thinner. For example, continental lithosphere averages between 40 and 280 kilometers in thickness, whereas oceanic lithosphere averages from 20 to 150 kilometers in thickness. So you can see continental lithosphere can be quite a bit thicker than oceanic lithosphere. The temperature of the lithosphere ranges from 5 to about 500 degrees Celsius. Of course, it's cooler on the outside towards the surface than it is as you go deeper through the crust. So the second layer based on physical properties is called the asthenosphere. This is a soft, weak layer that is just underneath the lithosphere. We call it weak because the rock there is close to its melting point but not completely melted, so it has kind of a gooey texture. This asthenosphere averages about 550 kilometers in thickness, and the temperature ranges from 300 to 500 degrees Celsius. The next layer down is called the lower mantle. The lower mantle is made out of rigid rocks, but they are very hot and capable of very slow flow. There are some rocks rising in the mantle, cooling and sinking in that process of convection, which we discussed when we were talking about the atmosphere. The lower mantle is about 2,250 kilometers in thickness on average, and its temperature ranges from 900 to 4,000 degrees Celsius. Next, we have the outer core of the Earth. This is a liquid iron and nickel alloy. It's liquid because of the very high temperatures found near the center of the Earth. It's about 2,260 kilometers in thickness, and its temperature ranges from 4,000 to about 5,000 degrees Celsius. An important thing about the outer core is that the liquid iron in it flows due to the rotation of the Earth, and this flow of liquid iron generates Earth's magnetic field, which protects us from radiation from the sun. Finally, we have the inner core. This is a solid iron-nickel alloy. It's solid due to very high pressures found here. It is hotter than the outer core, but as you compress things, the melting point increases, so it is solid even though it is very, very hot. It's about 1,220 kilometers thick, and it has a temperature ranging from 5,500 to 10,000 degrees Celsius. So the core of our Earth can get to be about the same temperature as the surface of the sun. So as we just saw, the core of the Earth can reach temperatures similar to the surface of the sun. So why is it that Earth's interior is so hot? There are two main reasons. First, the heat from the formation of the Earth, that process of accretion where all of the stuff clumped together. It's a really hot process that accounts for about 10% of the total heat inside of the Earth. And then the other important one is the decay of radioactive materials deep within the Earth. That decay process releases heat energy, and that accounts for approximately 90% of the total heat inside of the Earth. Okay, moving on to plate tectonics now. The main idea of plate tectonics is that the lithosphere or crust is broken into chunks that we call plates, and these plates are pushed and pulled around by convection currents that occur in the mantle and the asthenosphere, which you can see in this animation. Here's this process of convection. This rock is rising, and then as it rises, it diverges, and then the chunks of plate on top are being pushed and pulled on top of those convection currents. So let's discuss some of the evidence that we have that supports this idea of plate tectonics. First off, we have Continental Drift. So this guy called Alfred Wegener, you can see him pop up here every once in a while. He proposed the idea that the continents were once joined together into one big landmass that he called Pangaea. Initially, people did not accept this idea because even though it seemed like the continents did match up, like their outlines, he couldn't describe how the plate motion could have occurred. So here's some of the evidence that Alfred Wegener used to describe his theory of continental drift. So first off, there were matching fossils. So there are certain fossils that are found on continents that have an ocean between them of organisms that couldn't get across an ocean by themselves. So the first example we have is this Mesosaurus. It's a reptile that's a water reptile, but it doesn't have the type of appendages that it would need to swim across an entire ocean, and yet there are fossils of it found on the coast of both South America and Africa. So that explains continental drift because those land masses must have been joined in order for a mesosaur to be on both of them because it could not have swum across the ocean. And then a plant example is this Glossopteris. Glossopteris is this tree plant here. It had really big heavy seeds that couldn't like float across an entire ocean to colonize a new continent, but it's found all over the world. So it supports this idea that all of the land masses used to be joined together pretty closely so that those heavy seeds could exist on all of that land. Next piece of evidence we have for continental drift is matching rocks. So pretty much there are places on the Earth where we can see that there is a mountain range that looks like it's just been split in half by an ocean. So the best example we have is these mountains here, the Caledonian Mountains of Scandinavia and Greenland and the British Isles, are the exact same mountain range as the Appalachian Mountains of the east coast of the United States. They're just split apart by the Atlantic Ocean, so that supports the idea that all of this land used to be touching each other at one point when those mountains formed. Third piece of evidence that supports continental drift is the existence of ancient climates that we can see evidence of. So there's evidence of climates that would not be possible at the current latitude that the land is found at. So for example, there is evidence of glaciers on land that is now near the equator, such as this chunk of Africa. There's evidence of tropical swamps in what is now northern Canada, which now we know, of course, it's much too cold for there to be tropical swamps in northern Canada at its current latitude. And there is evidence of very arid, dry desert in the area that is now the Amazon rainforest, which we know, of course, is not a desert at this time. So other than continental drift, we've got another piece of evidence for plate tectonics, and that is called seafloor spreading. Seafloor spreading was kind of thought of by this guy, Harry Hess. He thought that these features called mid-ocean ridges, which are like kind of a mountain range in the middle of the ocean, he thought that they form new seafloor crust, and then at the edge of the ocean, old seafloor crust descends into what's called a deep ocean trench and gets destroyed. So some evidence that Hess used to support his theory of seafloor spreading. First, we have magnetic patterns that we find in seafloor. So periodically the Earth will reverse its polarity so that the north magnetic pole is down by where Antarctica currently is, and the south magnetic pole is up, where the North Pole, where Santa and all the polar bears are. So in the crust of the seafloor, we can see distinct bands of this mineral called magnetite. Magnetite lines itself up in freshly forming seafloor to point towards wherever the magnetic north is. And so we have this banding that shows that magnetite will line itself up to point towards the North Pole when it's being formed at the ridge. And then as it gets older and spreads away from the ridge, you get this kind of layered effect of magnetic patterns. Next, we have earthquake patterns. So deep earthquakes happen pretty much only at trenches in the earth. The shallow focus earthquakes happen all over the earth. That's like what we get here in Helena when we have an earthquake. But then there's these earthquakes that happen really, really deep in the crust, and those pretty much only happen at trenches where a chunk of seafloor is sinking down beneath another plate. And then lastly, we have ocean floor rocks, a couple characteristics of them. It's found that the youngest rocks are near where the mid-ocean ridges are, and the oldest rocks are near the trenches, which you can see in this diagram here. The red color is showing the youngest rocks found at all of these mid-ocean ridges on the planet, and the blue and purple are showing the oldest pieces of oceanic crust which are descending beneath these continents at trenches. And then also there's the fact that there's little to no sediment that is found near the mid-ocean ridges where the rock is young and hasn't been weathered, but then there's quite a bit of sediment that can be found by the time the seafloor has moved all the way from the ridge to the trench, there's quite a bit more sediment accumulation near the trench.